Hi everybody, Dr. White here to discuss bivariate distributions of the discrete type. Bivariate. So what do I have in mind here at the beginning of this chapter? Well, a bivariate random variable is an ordered pair of numbers as opposed to a regular random variable that's just a number that depends on chance. A bivariate random variable is an ordered pair of numbers whose values depend on the outcome of a chance process. Here's a more mathematically precise way to describe this. You've got the plane, the xy plane, which we can write as r cross r squared. All the points on the xy plane. Now imagine some subset capital S of that plane, okay? And let it be discrete, meaning that there is a smallest possible distance between any 2 points in that subset, okay? Let's have a function, little f of little x, little y, on capital S. And what it's got to do is satisfy that its values are non-negative for all the xy in S. Oh, and by the way, S will be called the sample space. And furthermore, if you add up f of xy for all of the xy's in the sample space, you get a 1. So the way we write adding up is we're going to use two sum signs. And then we'll put xy in element of S underneath. But you will think of this ultimately as like you're adding over the possible values of one of the dimensions of the ordered pair and the possible values of the other dimension. We'll see this in some examples soon. Anyway, that sum has got to be 1. Okay, so that's kind of like, so the first thing is like saying the chance of getting a particular xy ordered, sorry, that keeps happening. The chance of getting a particular xy ordered pair can't be negative, and something's got to happen. The sum of the chances has to be 100%. So if that happens, then we say that little f is the joint probability mass function for some bivariate random variable xy. So here's an example that's also in the book. Say that you roll a pair of fair dice, die 1, die 2. You roll them. And let's say the rolls are in the way that the dice land is independent of each other. Now, of course, they knock against each other as they roll, but that kind of knocking, in our experience, doesn't occur in such a way that when you know how one of them landed, that changes your estimate of the chances for the other one to land certain values. It, still 1/6 chance each one, no matter how the first one landed. So let's let capital X be the minimum of the rolls and let capital Y be the maximum of the two rolls. So X is the smaller, Y is the bigger of the two faces that land up. Now, I'm not saying right now that capital X and capital Y are random variables. I'm saying that we're looking at a bivariate random variable, parentheses, capital X, comma, capital Y here. And I want to figure out, based on the assumption of fair die and independence, what's a good choice for the probability mass function, the bivariate probability mass function. So let's think about this a bit. There's 6 times 6 equals 36 different ways for those two dice to land. And they're fair dice, so all of those ways are equally likely. So when it comes to finding the chance for getting any particular ordered pair, we just need to count up the number of ways to get that ordered pair and divide by 36. So here is the xy plane. And these dots here represent the sample space S, the possible ordered pairs for this random experiment. So for example, it is possible that your min and your max rolls were both a 1. That happens only one way, where they're both 1. And so 1 over 36 should be the F value for that particular point. Notice that the point 2, 1 is not in the sample space. You can't have your minimum be 2 and your maximum be 1. So you'll get things along this diagonal where your min and your max are the same number. And when you think about it, that means that both of the die had to be that same number, and there's only one way out of 36 for that to happen. So 1 over 36 are the probabilities, the F values, that go with those points in the sample space. Okay, now there's some other points in the sample space, and like here, in here, and so on, where the maximum roll was bigger than the minimum roll. Okay, and we need to find the F values for them. So like, what if the max was a 6 and the minimum was 1, putting you at the point 1, 6 right here? Well, there's two ways for that to happen. Die 1 could be 1 and die 2 could be a 6, or die 2 could be a 6 and die 1 could be a 1. But that's the only two ways. 2 over 36 is the chance. And when you work it out, for every other one of these points above that diagonal, the chance is also 2 over 36. I just really didn't have room to write all those fractions in my drawing here. But if I needed it as like a formula, I could do it. F of xy is piecewise defined function, which is 1 over 36 when x equals y, and it is 2 over 36 when x is less than y. Okay. So I said that capital X and capital Y here, that I'm not like claiming they're random variables. Not up front, but I'm going to show you that you can actually consider them as random variables. Define the following function, little f of capital X of little x, okay? And define it as you sum over all of the y's so that little x, little y is in the sample space, f of xy. So like if you wanted capital F of x where little x is 2, okay, then you would go to all the y values where 2, y is in the sample space. And so that would cover these points that I am marking out right here. And you would add up their probabilities. And here, again, I'm being kind of lazy. I'm just putting the numerator of the fraction for little f in the spot. And so I add those up and I get 11 over 36. Sorry, is that 11? No, oh, that's, sorry, that's an 8 plus a 1 is a 9 over 36, okay? So, intuitively what I'm doing here is I'm adding up the probabilities for all the different ways for capital X to be 2, So that ought to be the chance that capital X is 2. And similarly, for any of the other values of capital X, you just go to all the y's where little x, little y is part of the sample space, add up, and you get f sub capital X at that little x. Ta-da. So right here are all of the values of f sub capital X. And you'll notice that they're all 0. And also, if you add them all up, that would be the same as adding up over the entire sample space, which we already know is a 1. So the sum over all the x's of f sub capital X of little x has to be 1. So it does the two things that a function has to do to be a probability mass function for a random variable, okay? And similarly, if you define f sub y of little y to be the sum of the chances for all the different ways to get little y in an ordered pair, so you'd have to add up all of the x's where x, y is in the sample space, then would look like this. So for example, f sub capital Y of 5 would be the sum where x is 1, x is 2, x is 3, x is 4, x is 5 of those chances, and that again is 9/36. And same for all of the other little y's, okay? And again, you'll notice that they're non-negative and that they're just another way of adding up all of the little f's over the whole sample space, so they sum to 1. And so again, this is a real probability mass function for a real random variable. And so you can actually say that the x and y's here are random variables on their own right. It's just that their distributions come like in the margins of the picture for the distribution of the joint random variables. So we call them marginal random variables. So yeah, we define capital X and capital Y using the marginal distributions that we defined as random variables. Now that we know about them as random variables, let's grapple for the first time in a serious way with the idea of independence of random variables. So far, formally, we only have a definition for independence of events. But we've kind of been talking around the idea of random variables being independent of each other. Let's get honest and make a definition for it. So we say that random variables are independent if they're part of some joint distribution, and if you take the marginal for one of them at some little value, little x, and the marginal for the other, so this is the chance that capital X is equal to little x. This is the chance that capital Y is equal to little y. If you multiply those together, then you should get the chance that capital X is little x and capital Y is little I. What you're saying there is that the probability of this and is the product of probabilities, which aligns with how independence works for events. So this seems like a good definition for independence for random variables. So X and Y are independent if this happens for all the xy's in the sample space. If it fails to happen just once, then the random variables are not independent. So in our example, X and Y are not independent. We're saying they're dependent. All I got to do to convince you of this is to come up with one thing in the sample space where that product ain't equal to the little f. So I'm going to think about 1, 1 in the sample space. So f of 1, 1 was 1/36, as you'll recall. But fx of 1 turned out to be 1/36. Here's the fx. That's not right. That's 11/36. And fy of 1, so that's the chance of the max being 1. Let's see, what's the chance of the max being 1? 1/36. Oh, so got a little typo here. Well, not really a typo. I mean, what I wrote is correct mathematically, but it's misleading. I should have had the 11/36 here and the 1/36 here. So I'm going to correct that right now in my notes, and you'll see a corrected version when you look at this, if you look at the original PDFs. Okay, well, anyway, F01 is 1 over 36, but if you multiply these two things together, you don't get anything that reduces to 1 over 36. It's going to be 11/36 of 1 over 36. It's much smaller. So those two things are not equal, so the random variables are not independent. They're dependent. Another way, by the way, that you can just tell right off that these random variables are dependent is just looking at the sample space graph. Like if somebody told you that capital X were 1, had turned out to be 1, then anything from 1 through 6 would be possible for the max. You know, if the min is 1, well, the max still could be anything from 1 to 6. But if somebody tells you the min is 2, then the max can't be 1 anymore. It can only be anything from 2 to 6. So without even knowing the exact probabilities, you can see that independence fails here. A chance that was non-zero before is now 0. So that's a kind of quick way to see it. The only chance for independence is if you get kind of a rectangular shape for your sample space. All right. What about expected values, mathematical expectations for bivariate random variables? Well, let's go ahead and do a lot at once. So let's give ourselves a bivariate random variable with some joint PMF, little f, on some sample space S, some discrete subset of the xy plane. And let's consider some real valued function of two variables and look at the function of x1, x2. So, you know, for example, if your function is square the first one, add on the second one, then add the number 3, then your u of x1, x2 would be x1 squared plus x2 plus 3. Or if your function was multiply the x1 and x2 together and then, you know, multiply by 5, then this would be u of x1, x2. If your function was just given x1, x2, return x1, then that would be your u. In any case, what comes out here is a number. It's not an ordered pair anymore, it's a number. And so it's a number that depends on chance, because x1 and x2 depend on chance. So it's a regular random variable, like we defined at the very beginning of our work with random variables in chapter 2. So the definition for expected value of u of x1, x2 should be exactly as before. It should be the sum over all the possible values of the x1, x2 of u of that value times the chance of getting that particular ordered pair. So a very important special case of this, and there's a couple of important special cases, but the one we're going to talk about right now is when the u returns only one of the elements, the ordered pair. Like say u of x1, x2 is just x1. So the expected value of the u, and those should have been like capitals there. So let me go ahead and make that change. Okay. Would be the sum over all the ordered pairs in the sample space of the u of x1, x2, so it's the little x1, times the chance of getting exactly that ordered pair. And you can separate this out. So what you could do is you could sum over all of the values that x1 could be. And then for any given x1, you could look at all of the possible x2 values that there are that go along with that x1. And you would do x1 times f of x1, x2. So like I'll just pop up to the initial example again. So like if you let x, you know, it could vary from 1 to 6, okay? And when x is 1, you're going to be summing y goes from 1 to 6. Now, when x is 2, you're going to be summing 2 to 6. And when x is 3, you're going to be summing 3 to 6. So in a specific case, you can actually be more specific about how this sum gets written out. It would look like sum x goes from 1 to 6 of the sum y goes from x to 6. So, well, anyway, when you're in this sum and you look at it, this inner sum here, the only thing that's changing is the x2. x2 is a constant as far as that inner sum is concerned. So it can be factored out like this. And then when you stare at that inner sum, you realize, oh, that's just the definition for the marginal of capital X1 at little x1. And so your sum becomes sum over all of the possible values for little x, for capital X1, of the value times the chance of that value, which is the expected value of x1. So no surprise, when your function is just x1, the expected value of x1 computed using summing over that whole two-dimensional space is the same as what you would get if you just looked at the marginal for x1 and summed up along the x's the usual way. And you're going to get a similar result if your function of x1, x2 is the second member of the ordered pair. So what we're showing here is there's two ways now to get expected values for marginal random variables. You could do a double sum over the entire sample space of the bivariate random variable of which your marginal is a part. That's this. Or you could find the marginal for your marginal, you could find the distribution for your marginal random variable and compute the expected value the old way. Okay, let's just do another exercise. This is exercise in the book, number 3. It's another little example of a discrete, bivariate distribution. So the formula for it is this. F of xy is always x plus y over 32, where x can be 1 or 2 and y can be 1, 2, 3, or 4. And so you see this time we've got a rectangular shape to our sample space. 2 wide, 4 high, as it were. 8 total points in the sample space. And I haven't drawn the points, but I've drawn the f values right at the points. So for example, when x is 1 and y is 4, then you get a 5 over 32, and so on. And I've also gone ahead and summed up for each x the possible y's so as to get the marginal distribution for x, and over here is the marginal distribution for y. And let's just play around and get some probabilities, okay? So like, what's the probability that x is bigger than y? Well, let's see, x can only be 1 or 2. So for x to be bigger than y, x has to be 2 and y has to be 1. That is it. And so it's just going to be 3 over 32. How about the chance that y is 2x? Let's see, which elements of the sample space correspond to y being 2x? Well, when x is 1 and y is 2, y would be 2x. And when x is 2, y is 4, y would be 2x, and that appears to be it. So we just add up those two values, those two f values. So when you're getting probabilities for events for a bivariate random variable, it's just like before. It's like finding areas underneath, but now I should think it's more like volumes underneath something over some little area, and the area is the event. Like the event is now not a one-dimensional thing, it's this little subset. of R2. Sorry. What about the chance that x plus y is 3? So let me see. X could be 1 and y could be 2. X could be 2 and y could be 1. That's it. There's just two things. You find the probabilities, you add them up. 6 over 32. What's the chance that x is 1 and y is 1? Oh, let's see. I guess that's just one thing. And that would be, yeah, 1 plus 1 over 32. What's the chance that x is 1 times the chance that y is 1? So this is different. I got to find the marginal where x is 1. So I head up and, that was where I added and got the 14 over 32. And similarly, what's the chance that y is 1? That's 5 over 32 when you consult that marginal. Yeah. And when I multiply those two things together, I get 90 over 32 squared, which I can write as 2 over 32 times 45 over 32. So I can see that that product, no way can it be 2 over 32. It's a little bigger than 2 over 32, because 45 over 32 is a little bigger than 1. So the probability of this and is not equal to the product of the probabilities, so the x and the y are dependent. So even when the distribution is rectangular and the formula for the little f looks kind of like symmetric in the x and the y, like x plus y is y plus x, doesn't matter if you switch them, still the distribution might not be, the marginal random variables might not be independent. Independence is like kind of rare in a sense. If you just like grab the bivariate distribution at random, if that were possible, then almost certainly it would be dependent marginals. Another important kind of mathematical expectation would be for the variance of the marginal distributions. So like, how would you get the variance for, let's say, the capital X in this example? So you would sum over all of the possible values in the sample space. The X minus the expected value of X squared. Oh, I'm sorry, I'm getting ahead of myself. I haven't found the expected value. So let's go ahead and find the expected value of X. So that's the sum over the sample space of X times F of X, Y. And so we sum, what do? We could start with the X's, we could start with the Y's. It doesn't make a difference. I'm going to start with the X's, and I say possible values of X are 1 and 2. So sum, X goes from 1 to 2. And no matter whether X is 1 or 2, the possible values for Y are 1, 2, 3, 4. So we'll have a sum, Y goes from 1 to 4. And then we'll say little x times the chance of getting that ordered pair, x, y. So I'm doing the regular long way using the definition of the expected value of u of x1, x2. So that would be like 8 different things that I have to add up. 2 times 4 is 8 things. That's a lot of summing. I'm a lazy guy. After all, I found the marginal distribution already. Then I only have to add 2 things. So I'm going to go ahead and get expected value of x the shorter way, sum over the possible x's, x times the marginal. So 1 times the chance of getting a 1 for your x, 2 times the chance of getting a 2, and it reduces to 25 over 18. Now I'm ready to try the variance. So one way is to think of the variance as a u of x1, x2, that's just the x1 minus its mean squared. And so you sum over all possible things in the sample space. That's a typo. That should be a 4 there. So let me fix that. Okay, yeah. And here we are with our x minus our expected value squared, and here we are with our f of xy. So we could do that, but I've got the marginal, so I prefer the marginal. I'll sum over possible values of x minus its expected value squared, marginal. So a little bit quicker work, and I don't even care to reduce it. Let me throw another example at you because it gives you a window on a kind of a generalization of binomial distributions. Say that you've got a spinner, okay, this little circle here, and like attached to the very center of the circle right here is like one of those little spinner arrows, and you flick it with your thumbnail or your fingernail, and it spins. And say it's equally likely to land at any angle, to stop at any angle. And so the chance that it lands in these three regions would be proportional to the relative areas of the three regions. So let's say that the chance that the spinner lands on region A is some number p sub A between 0 and 1. Chance that you land on B is some number p sub B between 0 and 1. And of course, those two would have to add up to less than 1 because there's a chance of landing on C as well, which we'll call p sub C. So those are supposed to be little p's. They're not right here. They're not doing a good job of looking like little p's, but they are. Whereas these are capital P for probability. And let's say that you spin n times and all your spins are independent of each other. And let's let capital X be how many A's you got, what B's you got as capital Y, and how many C's you got as capital Z. So this would be like an ordered triple. So it looks like a trivariate random variable, but not really, because if you know two of them, you get the third, because the third has to be n minus the others, because you have a total of n spins. So I'm just going to notice that Z is n minus x minus y. So really, the randomness could be thought of as all there in the XY ordered pair. So bivariate, random variable. And let's see if we can get the bivariate PMF, little f of xy. So what's the chance that x is x and y is y? So that comes down to saying the chance that x is x and y and y, and y is y, and z is n minus x minus y. So in order to get that, you'd have to get the a x times. And here's the chance of getting like x a's in a row. And you have to get the b y times. Here's the chance of getting b y times in a row. And you'd have to get the c n minus x minus y times, and here's the chance of getting that many c's in a row. So the product of these three things is the chance of getting, first of all your xa's, then all your yb's, and then all your n minus x minus y z's. So that would be like one way to get this event to happen. But there's a lot of ways for the event to happen, and how many ways are there? Well, it would be the number of ways to spell a word where the letters you're given are xa's and yb's and n minus x minus yc's. There's how many ways can you rearrange those to make a word? So this comes down to that same Mississippi problem that we did way back. And you remember it's going to be the total number of letters in factorial over the factorials of how many of those letters are the same. And so by commutativity of multiplication, all of the probabilities for those ways are going to be the same as that probability of like getting them totally in order, like all A's, then all B's, then all C's. Each of them is going to have that probability, and so the total probability is just the number of ways times the probability that I've got selected. So that PMF there is an example of what we call a trinomial distribution. So to get a trinomial distribution where there's like 3 possible outcomes for your random experiment, and you're doing your experiment n times and just like tallying up what happened, you only need to specify 2 numbers. You need to specify the chances for 2 of them to happen, and then you can pop it out and use this formula. Okay, that is it for this section. I will see you again soon.